What we developed in the first part of, well, in the second part of this unit, but in the last two chapters, was how do the graphs of sine and cos look? How can you do all the transformations with them? And so what we find is anything that happens in real life that is cyclical in nature will have a graph that follows a sine or a cosine. And so what we're going to look at today is some real life examples and how you can use those examples to create equations, graph those equations. Example 1 is the easiest type because they give you the equation in the question. So the depth of water in a harbor is given by this. Why is it sinusoidal? Tides come in and out. We live in Winnipeg, not near an ocean, but you guys have heard about tides, and you know that they come in and out, and they keep doing that over and over again. And they are very predictable. In fact, so predictable that you can make an equation that models the situation, and you can figure out how deep the water is going to be at different times. So this one, they've got the equation, and the first thing they want us to do is sketch the graph. So I'm going to rewrite it here. We've got negative 4.5 cos 0.16 pi t plus 13.7. Using DAB C and thinking about each of these things, can you see that as a starting point, your center line is at 13.7. Okay, it's a real life example, so it's not necessarily a pretty number at 13.7. And our amplitude is 4.5. So with the DAB part, before I put it in, I'm going to sort of think about my scale a little bit. I'm going to put 13.7 right there, which means I'm going to need to go up 4.5 and down 4.5 from there. So I'm going to estimate, looking at my scale, about what 4.5 would be. If I go up 14.5, I'm going to go up to 18.2. Down 4.5 is going to give me 9.2. So my center line, I can draw it in there, is going to be at y equals 13.7. My b value is 0.16 pi, which isn't a very nice looking number, but I can find out what my period is because my period is always 2 pi divided by my b value. This would be a calculator question because of those numbers. And if I calculate that, you get 12.5. So on our axes, we can label 12.5 and divide it into 4 equal sections, just like you were doing this morning. Half would be 6.25. Half of 6.25 is 3.125. Add 3.125 to 6.25, and you'll get 9.375. Next, you would graph it without the shift, but can you see that our equation has no shift at all anyways? And so when we graph it without the shift, it's going to actually be our final graph. Where does a cosine graph start? At a maximum, but you see that there's a negative in front. And so that negative would be a vertical reflection. So instead of starting at the maximum, it starts at the minimum. So we would go minimum to center line to maximum to center line to minimum. And we can create our graph. part B to the question says, a bulk carrier needs at least 14.5 meters of water to dock safely. For how many hours per cycle can the bulk carrier dock safely? In other words, a big boat needs a certain amount of water in order to come into the harbor. If there's not enough water, it's going to bottom out. It's going to hit the bottom of the ocean and get stuck. So it's wondering, how long can this boat come into the harbor and go out again? So on our diagram, if we look at our picture that we've graphed already, and I label where 14.5 meters, maybe we should label this. This is depth, and this is time down here. We need a depth of 14.5, which would be about here. If I draw a line straight across from there, can you see from that line that between this point and this point, that's when the water is deeper? Anything before that or after that, the water wouldn't be deep enough, because the ship or the boat needs at least 14.5 meters of water. So for solving this, we're going to look at solving this in two different ways. We're going to look at solving it using technology, and we're going to look at solving it algebraically. So first of all, with technology, you would need to have a graphing calculator. And we're going to put this equation into our graphing calculator and see what this looks like. So the first thing we're going to do in our calculator is type in our equation. So I'm going to go and click on the y equals button. If you have anything else in there, you can clear it out. And my calculator says that we're in radians. That's going to be important. Our graph needs to be in radians as we go along. Battery's dead? Yes. Okay. So we've got y equals negative 4.5. We've got to hit the negative button. Negative 4.5 cos 0.16 pi, and then x bracket plus 13.7. Now, if you just type that in and push graph, probably this is what you'll see. Most people's calculator will be set up just to see that little tiny bit. What we want to do on our calculator is we want to set it up so it looks exactly like this screen that we have here. So what we need to do is we need to make our calculator screen like that. Currently our calculator screen is down here, seeing that part, right? We just have that little loop at the top. We need to move this screen so we can see this. Well, the graph that we did by hand tells us what we need our window to look like. Can you see along our x values that we need to see a little bit past 12.5? On our y values, we need to see up to 18.2. So the way that we can do this on our calculator is our calculator has a window button. If you hit that window button, it tells you where it's looking right now. It's looking at negative 10 to 10. What did we want to see? We wanted to see just a little bit of the negative, maybe negative 1, and past 12.5, I'll go 15. This x scale, you can leave it at 1, But do you see how we had each of our ticky marks at like 3.125? If I change that to 3.125, it'll have marks exactly like I had on the bottom. For my y minimum, I just need to see -1, but I need to see up to 18.2. So I'll go up to 20. It's hard here to do a scale that matches ours, but maybe we want to go by 5s. Now if I hit graph, the scale and the graph looks a lot like mine. I've just drawn this scale. If I want to add this black line in at 14.5 meters, I can go back to my calculator, go to y equals, go to a second equation, and type in 14.5. That will draw a horizontal line where 14.5 meters is. The question was asking, for how long can it dock safely? We want to know how long it is from this point to this point. Here, I'll go back to that question. Okay, this is a really cool option where you take your graph, right? Just drag it onto your notes. There's our graph. We want to find out what time is this and what time is this. Again, your graphing calculator has a lot of stuff built into it. If you go second, calculate, you can find number 5 where they intersect. And when you get to the intersect, which is your first curve? It's the blue one. Enter. Which is your second curve? It's the red one. Enter. Guess where you think they're going to intersect. And your calculator will always find the one that it's closest to. So push enter, and it finds that one is at 9.02. If I want to find the other one, I would repeat this process. Second, calculate number 5 where they intersect. But I just have to make sure I use the arrow over keys. So now my cursor is closer to the other one. If I push enter on the first one, enter on the second one, and enter on the third one, it finds at 3.48. So it's safe from 3.48 hours until 9.02 hours. The question asks, for how many hours per cycle can it dock safely? If I go 9.02 minus 3.48, since it's a word problem, it can dock safely. For 5.5 hours. Now, in many university classes, you are not allowed to use a graphing calculator to solve. You have to be able to solve things algebraically. So I'm going to show you how to solve it algebraically. It'll be on the video, but I won't give you enough time to write it all down. So right now, just watch. If you want to write it down on your own later, you can go back and watch the video. But the idea for solving this algebraically is we know the depth has to be 14.5, so we would put that in for our y value, or for our depth, into our equation. Can you see the only thing you don't know is t, and that's what you want to solve for. So now you just have to use your algebra skills to get t by itself. Okay? Where is the t? It's inside of cos. So to start with, I'm going to rearrange things to get cos by itself. Subtract the 13.7, divide by the negative 4.5, and then cos is by itself. Now, what makes this difficult at this moment is inside, we've got a bunch of stuff inside of cos. If this question was just cos theta equals, you'd be like, I've done those before. I can use my cast rule, I can find my reference angle, and I can solve. So what we do in math sometimes is we do something called a substitution to make our question look easier temporarily. That substitution just looks like this. If instead of having all of this inside of cos, I'll call that theta. Theta is equal to that. Because then my question is just cos theta equals 0.8 over negative 4.5. And that looks like something I've solved before. Well, how do I solve something like that? I find my reference angle by doing cos inverse. Remember, when finding your reference angle, you always do the inverse of the positive ratio. And I get a reference angle in radians of 1.392. Well, if that's my reference angle, what's theta? Cos is negative in quadrants 2 and quadrants 3. So you would find your answer in quadrant 2, right? Pi minus your reference angle. In quadrant 3, you'd go pi plus your reference angle. And so what we've done is we solve for theta. Theta is equal to 1.7495, and theta is equal to 4.5337. Okay? A little reminder, what did we do? We had made theta is actually equal to this. And we still want to find t. So now instead of saying theta equals 1.7495, we can say 0.16 pi t is equal to 1.7495. Could I get t by itself? Yes. Now that's easy. I can just divide both sides by 0.16 pi, and there's the 3.48. That matches up with the 3.48 we found right here on our calculator. We take our second angle of theta in quadrant 3, make it equal to the 0.16 pi t, divide and do the same things, and we get our 9.02. That matches up with the 9.02 we found here. So this, all of this stuff, you could do and could solve with just a scientific calculator. The other one is a lot quicker if you have a graphing calculator. But if you have a graphing calculator, you need to know how to make the window so it matches up and be able to use the tools where they intersect to figure it out. All right, let's go to example 2. A Ferris wheel has a radius of 15 meters and rotates once every 20 seconds. Passengers start on the bottom of a Ferris wheel, which is 1 meter above the ground. So I'm going to draw a picture of this because not everybody knows what a Ferris wheel is. This is when you go to the fair. I'll draw, so we've got move it down a bit here. There we go. Of course, it needs to be connected. There we go. This is the ride where you have chairs. Oh, you're having so much fun. And you go around and around. So we've got our Ferris wheel, and we're given some information, and we need to graph it and find its equation. It has a radius of 15 meters, so we know from here to here is 15 meters. That would be the same from here to here is also 15 meters. We get on the Ferris wheel 1 meter above the ground. And passengers start at the bottom, and it takes 20 seconds to go around. So right beside this picture of the Ferris wheel, I'm going to draw my graph. I'm going to put my ground here. I'm going to put time here and height here. We get on the Ferris wheel 1 meter above the ground. So here at 1 meter is where you're getting on. It doesn't make sense to get onto a Ferris wheel at the top. And it says 20 seconds later, you go all the way around. So if I mark 20 seconds on here, I would know I would be back at 1 meter at 20 seconds. Question, how high above the ground would you be at 10 seconds? Okay, where would you be? This is you. I'll draw. There you are. You're so happy to be on this ride. Here you are. You're starting at the bottom. 20 seconds. Oh, I didn't want to do that. There we go. 20. Come on, guy. Oh, man. It's not being very... There we go. 20 seconds. You would go all the way around. 10 seconds, you'd be where? Right there at the top. Scariest spot. So high up. Okay? What is that top? How high above the ground are you on this Ferris wheel? Okay? The radius is 15. We started at 1. Would you agree this would be up 15? And another 15 up. Right here at the top, you're 31 meters above the ground. That's going to be your maximum. 10 seconds, you're at that maximum, 31 meters. Five seconds, you would be right there. At 5 seconds, you're right in the middle, which is 16 meters above the ground. Can you see that that's your sinusoidal axis? And in fact, we could divide this into 3 equal sections, and you go from the bottom to the middle, to the maximum, to the middle, to the bottom, and this is the path of the Ferris wheel. It makes a nice sinusoidal curve. So given the situation, they gave us a starting point and a period, and knowing that it was cyclical in nature, we can draw a sine or cosine curve for this. Now the question says find that equation. Well, to find the equation, again, we can think of dab C. Do we know our D value? Do we know our center line? Yes, it happens to be at 16. Do we know our amplitude? How much from the center line to the maximum? That's the same as the radius of a Ferris wheel. It's going to be 15. And can we find our B value? Our B value, there's a formula for that. Our B value is always 2 pi divided by our period. So in this case, our B value is 2 pi over 20. And yes, you could reduce that, but I actually like it not reduced because if it's in this form, you can see the period is 20 really easily from that form. If you reduce it to pi over 10, it's not as easy to see that the period was 20. And the C value varies depending on what you decide. So here are some examples. You start by deciding I want to write a sine equation. My amplitude is 15. Sine, my B value is 2 pi over 20. And my D value is 16. We'll start with purple. Where does a sine graph start? A sine graph, and this is the language I've been using all the time, a sine graph starts in the middle going up. Do we have a place on this graph where the graph is in the middle going up? Right there, I'll label it in purple. Where is that point? Shifted 5 to the right. So if I want to write a sine graph, how do I shift something 5 to the right? Minus 5. Let's say we wanted to do a cos graph. Well, it still has the same amplitude. It still has the same period, so the B value will be the same. It still has the same sinusoidal axis. The only thing that changes would be where we start. I'll do this one in orange. Go back to our graph. Where does a cos graph start? Right, at a maximum. Where is that maximum? Shifted 10 to the right. How do I show a translation of 10 to the right? Minus 10. Those are two examples. Those aren't the only examples you could have. Right? In our activity this morning, you did negative sine graphs and negative cos graphs. In fact, for this graph in particular, I think a negative cos graph makes a lot of sense. Where does a negative cos graph start? At a minimum. And if we started at the minimum, there's no shift left or right whatsoever. So if I wanted to write a negative cos graph, amplitude still 15. Period is still 2 pi over 20. You don't have to write x minus 0. You could just write x because there's no translation left or right. But that would be another equation. If you typed in all three of these equations into your graphing calculator, they would produce the same graph every single time. So the next thing I want you to do is take out your calculator, and can you get this with this window, right? I want to see this window on my screen to show up. You can choose to write any one of those three in. I'm going to choose clear, clear. I'm going to choose the negative 1. And after typing it in, I'm going to go to my window and say for my x, I need to go up to 20, so maybe I'll go just a little bit further. My scale, I'll go by 5s. Maximum was at 31, so I'll go a little bit higher there. And hit graph to get our equation. Now for parts B and C, it says estimate the height after 22 seconds. So estimate means you don't have to get it exactly. You look on our graph here, 22 seconds would be about there. You go up, go over, and do an estimate. According to my graph, it looks like maybe at about 4 meters. I'm not sure. Okay. Problem with your graph is if things are not quite to scale, your estimate might be not the best. If you have typed it into your calculator can find it out exactly for you. Again, you can go second calculate, and here we want to find a value. What's our x value when x is 22 meters or 22 seconds? 3.86. Oh, my estimate was good. So the actual was 3.86 meters. Okay, same thing for C. Estimate at what time you'll be 20 meters above the ground. So I go to my picture here, and at 20, which is about here, that time and that time. So I'm going to say if I say 7 seconds, okay? Let's say I tell you this one is at 7 seconds, and I tell you it's right. You should be able to tell me exactly where this one is because of symmetry. If this one's at 7 seconds, this one should be at 13 seconds. 2 seconds after this, 2 seconds away from this. Now, we'll find out what it is exactly. So these are our estimates. And if we want to find the actual ones, we'd have to use our calculator. We need to go to y equals, and in our second equation, type in 20 to draw that horizontal line at 20. Second, calculate the intersection, number 5. Enter, enter, enter. 14.14. So we should be able to figure the other one out without going to our calculator. Do some mental math, figure it out, and I'm going to verify it here with our calculator. If one of them was 14.1, the other one is 5.9. So again, our estimates weren't bad, but the actual ones were even better. One more example that we're going to do on our own, and then there's a couple for you to try. World's highest tides occur at the Bay of Fundy, and again, they're periodic in nature, so they can be graphed with sine and cosine. And this example shows you the minimum amount of data that they would have to show you in order to create the equation. In this example, they tell you where a maximum is and where the minimum is. So if we draw a picture or a graph of what's happening, again, we're going to put time down here and depth here. At 4:30 a.m. we have a maximum of 8. So I'm going to put 8 up here as a maximum. How should I put 4:30 a.m. on my time? Does your calculator let you put in minutes? No. So what would be a good way to represent 4:30? Okay, if this is 0, 1, 2, 3, start with 4. Does 4.5 make sense for 4:30? Because 30 minutes is half an hour. So we have one point right here at 8. Then we have a minimum at 2 meters, 6 hours and 12 minutes later. So if this is 4 hours, 6 hours and 12 minutes later we'll be there. 10:42. If I put 4.5 for 4:30, what should I put for 10:42? How do I figure that out? Is it going to be more than 10.5 or less than 10.5? More, because 42 minutes is more than half an hour. How do we figure out that decimal? You can use a calculator. If you had a calculator, how do you figure out that decimal? Divide. Divide what? 42 by 60. 42 by 60. Mental math? Or is that a calculator one? What do you think? Okay. Calculator one, you get 0.7. Mental math, divide them both by 6. That would give you 7/10. Can you see you could have done that mental math? 0.7. So this is at 10.7. And at 10.7, we hit our minimum at 2. And those are the only two values that are given to us. But if it's periodic, it's making a sine curve. You know the following. You know that the next maximum is going to be right there. What value should I put right there? $16.9. How do we figure that? Well, from 4.5 to 10.7, that's 6.2. If it's periodic, it would take the same amount of time to get to the next maximum. From one maximum to another maximum, that would be one period, which in this case is 12.4. Whenever we draw a sinusoidal curve, we always split it into 4 equal sections. So the sections that we're missing are this one and this one. Half of 6.2 is 3.1, so 7.6 and 13.8. And those ones will be right on our sinusoidal axis in the middle. What is our middle value going to be? Y equals 5, halfway between 8 and 2. Wanted to label 5 on there, you could. And so we have this point and this point. You could even go back another 3.1 to this and say 1.4 if you would like. So again, we take the information. All we were given was a maximum and a minimum, but because we know how a periodic function works, we can draw the rest of it. Now the question A says after graphing it, we need to come up with an equation, one with sine and one with cosine. So again, right, we can think backwards from dab C. The C is what's going to vary depending on sine and cosine, but the D, the A, and the B values are going to be the same no matter what graph you look at. Can you see your center lines at 5? What's our amplitude? 3. Our b value, our formula for our b value is 2 pi over the period. Our period is 12.4. 2 pi over 12.4. So we now can go and write our sine graph. So amplitude 3, sine, b value, 2 pi over 12.4, x minus something, and our d value plus 5. Where does the sine graph start? In the middle going up? You have a choice. You could either choose this one or you could choose this one. Both would be right. So if I choose the first one, it's a shift of 1.4 to the right. If I choose the second one, it's a shift of 13.8 to the right. So I can just show that minus 1.4. If I go to do my cos graph, again, the amplitude is 3. Period is still the same, so my b value is the same. D value is the same. What changes is where I start. Where does a cos graph start? At your maximum. Your maximum is 4.5 to the right, or you could use 16.9 to the right. That would work as well. So now we've got two equations. Part B says estimate at 1:30 p.m. Where does 1:30 p.m. show up on our scale here? The 4.5 was 4:30 a.m. Where's 1:30 p.m. going to show up? At 13.5. 13.5, right there, my estimate would be 4 meters. So, with that, there are 2 at the bottom of this package which you can try on your own. And then, out of your textbook, which is section 6.7, starting on 548, if you want more word problems to practice, there's a lot more there. You can try questions 3 through 9.